introduction. Today I'm going to talk about some of the work we did in the past couple of years analyzing random feature model and related kernel method. And the main message that I want to convey is that there is some interesting universality phenomena that we can exploit in analyzing these models. I'd like to start this talk by showing a very simple numerical experiment to illustrate what I mean by universality. Suppose you have you want to construct a matrix, n by n matrix, and you just populate each entry with independent random variables. It doesn't really matter what type of distributions these random variables come from. You only want to make sure that they have a mean zero and a unit variance, right? And you populate these matrices, these entries, and because this matrix is not symmetric, eigenvalues are complex valued. So you plot the resulting eigenvalues, and here we choose n equal to 2000, and this is what you would get. Of course, this is a classical circular law, right? Eigenvalues, densities of these eigenvalues essentially form a uniform distribution over this unit circle, right? And this is a simple example of universality because here you are not specifying any distributions on these entries. You only need to control the first two moments of these given quantities, right? And the detailed construction of this matrix doesn't matter. But there is actually more to the story. What about a deterministic matrix? So here, instead of having random entries, let's just fill A with first 4 million digits of pi, right? So of course you have to do normalization. You want to make sure that the empirical mean is 0 and the empirical variance is also equal to 1, and you can compute a plot of eigenvalues, and you get the same type of uniform distribution of the circle, right? You can see that universality is pretty robust. The randomness is just a device for us to understand this universality phenomena. Now, in general, universality refers to the observation that many large and complex models are asymptotically equivalent in terms of their microscopic properties, although they can be very different in their constructions. I'd like to argue that universality is one of the blessings of dimensionality because of this diagram. Suppose you want to understand or analyze a given system A, but for some reason you don't know how to do it. But then, if you can show A and B and C are in the same universality class, you can study system B instead if it is easier to work with. And whatever property that derive out of B can be transferred to A because of universality, right? And what I'm going to show here in this talk is an instance of this exploiting universality for analyzing learning by random features. And this is the work done with my students. First, just recall for basic setting, we are talking about the supervised learning setting, where we're given a collection of training samples, xi, yi, and they want to learn a correct classification of these data sets. Now, the simple setting is these data sets are linearly separable. You just need to learn a linear classifier, and you can do it by solving an empirical risk minimization problem, where W here is a variable that you want to learn, and you can call it weight vector, and the W essentially encodes this separating hyperplane, right? And in this optimization problem, L is a loss function. You can have different choices of loss function, square loss, logistic loss, and so on. And R is a regularizer. You can also have different type of choices, right? But in many cases, the actual input data are not linearly separable. They are separated by some nonlinear surface. And the common idea is to try to lift the input data onto a high-dimensional space via some mapping T. You can call it so-called featureization map. The idea is that in a high-dimensional space, there's more room for all of these points. It's more likely for these points to be linearly separable, right? And a popular, very convenient way of doing this nonlinear feature map is just to implement everything in terms of a neural network where you pass your input data through some matrix multiplication and nonlinearity. You can do it at multiple levels. At the end, you have the feature vector, right? And then you do a linear classification using these weights and to try to separate these two classes data. And again, this problem can be formulated as an optimization problem, but in this case, in addition to learning the linear classifier at the last layer, you also learn the parameters of the feature gradation map F, right? So it's an optimization problem. But we're going to consider a simplified version of this so-called random feature model, and this is proposed by Brahimi and Rat as a way of efficiently approximate kernel method. And the idea is random feature model is the following. Instead of trying to learn the feature map F, let's just assume that the weights of the neural network at the first layers are random and they're fixed. So you just draw these, but you don't do any further optimization. What you do is to only learn the weight vector at the second layer or the last layer, right? This is also was proposed under different names, extreme learning machines and so on. Now, in terms of optimization problems, you can think about F, the weight matrix in the first layer to be fixed, random but fixed, but then you learn the weight W, and then it's the same optimization problem where L can be any loss function that you choose. Right? Okay. So we want to do theoretical analysis of optimization problems like these. So what are the type of questions that you want to answer, or quantities that you want to compute? The first type of quantity that you want to compute is the training error. Okay, so that means if you get to solve this optimization problem, what is the minimum cost that you would achieve? And there is also the test error. Suppose you have learned optimal classifier, the linear classifier, and then you have a new sample. What is the classification error and so on? Okay? And here we use the notation A to represent the vectors that comes out of this random feature map, right? First, if you want to, depends on how detailed you want your analysis to go. If you want to have precise information of these two quantities, then typically you have to make some additional statistical assumptions on how the data are distributed. A common assumption is to assume your incoming data X and Y are independent Gaussian vectors with some covariance matrix. And you also assume how initially the labels are generated, for example, by a student-teacher model. These are also classical settings. All right, and then you can do analysis. And for a special case, so this is the feature map, and sigma here represents the nonlinearity that you apply. If sigma is a linear function, then this feature map is just a linear feature map. And then because we assume X and Y are Gaussian and the feature vectors are still Gaussian, right? And then this boils down to analyzing high-dimensional optimization problem involving Gaussian random vectors. And here's a list of tools that you can use, starting from the replica method from statistical physics. But then you can have other versions of more rigorous methods, for example, Gaussian width, Gaussian comparison inequality. If you are dealing with a convex optimization problem, you can also analyze optimization problem by analyzing dynamics via approximate message passing. You can also do V1 out analysis. The point I want to make is that you already have a very rich and powerful set of tools for analyzing these problems, and this is essentially a playground for theorists. There are a lot of different questions you can answer. For example, the inference of the covariance of X, the performance, learning performance, and so on. Okay. But the challenge here is that if you have a nonlinearity in your feature map, right? So X of I, again, you get to assume it's Gaussian. F is just a fixed random matrix. But then what if your feature vector is a result of applying a nonlinearity element-wise on these F of Xi, right? And then this breaks the Gaussian distribution, and then you cannot directly use the previously mentioned tools that were developed for the Gaussian distribution.
So you have the next question. So are you going to talk about modulation for this model, or is it?
This talk is about essentially how you would analyze it. Yes. So I will not talk too much on modulation.
Okay. No, I'm just curious. Like, is it trying to explain some behavior of some more complicated models, or are you actually advocating, or are they actually advocating?
So I'm just saying
this?
Yes. So to me, what motivation is the random feature model is an approximation of the kernel method, and then you want to analyze the random feature model, and some of the tools that you use in analyzing this problem can also be used to analyze kernel methods. They're essentially very similar type of mathematical.
Do you already analyze kernel methods? Okay, I don't know.
So yeah, I can't, some of the two, because the kernel method and random feature model, the common technical challenge, mathematical challenge is nonlinearity. If you have linear functions, then all these problems are pretty standard. Yeah. So what I want to show, main point is there is a way, a very simple way of getting these nonlinear. Okay. All right. All right. Good. Okay. So the point here that I want to make is that you get to analyze the kind of linear feature map in a different way. So here on the left we have a linear feature map, right? And X is the input data vector, or if you have a multiple input data, it's a matrix. And then A is just the feature matrix where each column is a feature vector. All right, and then we can consider a different version that's called B, and B is a different type of feature map where you have f times x. This is essentially a linear transformation of the original data plus a constant. But then you also add z, which is an independent Gaussian matrix. So we can think about B as a linear feature map, but it's noisy. So it's a noisy linear feature map. Right? We have two versions: nonlinear versus a noisy linear feature map. And here, mu0, mu1, mu2 are three scalar coefficients that you can compute from sigma. I'll come back to this point, but so far we can consider these as coefficients that are functions of the nonlinear function sigma. Okay. And then for these two versions, you can calculate the corresponding training error A, training error B, and testing error A and testing error B. Okay. And there is this equivalence phenomenon. And at a high level, what we're saying is for a generic F matrix, you don't need to assume F to be random. F can be deterministic, but you have to be it has to be generic. I'll come back to exactly what we mean by generic. And for reasonable nonlinearity sigma, the training and testing errors of these two models, A and B, are asymptotically equivalent. So this is a phenomena, and I want to emphasize that this phenomena was observed in the literature a long time ago, and these are the papers that observe this phenomena in the context of regression or learning, but similar phenomena were known in the random matrix setting. For example, instead of looking at these A and B as a feature matrix, and then you want to understand training and testing error, you can think about A and B as just two random matrices, and then you want to calculate their asymptotic spectrum, and then you can very easily see that A and B have the same spectrum if you just do experiments, right? And there is these related work, a random matrix theory study, some versions of A and B. For example, in the paper by Chen, singularly considered a symmetric version, which is more related to the kernel method version. Okay. All right. But the challenge here is that the phenomenon is more general than just a spectrum of A and B matching, because if you want to study the spectrum of these two random matrices, then essentially you just do calculate resolvent, which has explicit formulas for a lot of quantities. But here, if you want to understand training and testing error, the loss function do not need to be quadratic. And then, in this case, these quantities are nonlinear and implicitly defined functions of these matrices. Yes?
The equivalence, I think, isn't it that the proportional asymptotics is
yes.
very important?
In proportional, yeah, but there are possible generalizations. It's yes, indeed. All these words all considered proportional asymptotics.
What do you mean generalizations?
For example, you have a polynomial scaling and so on. So,
oh,
yeah.
you're going to talk about that.
Maybe we could. Yes.
Okay.
Okay.
Thank you.
Okay. So it's a very similar idea. All right. First point, suppose before you prove it, how do we exploit this asymptotic equivalence? So, because if you get to assume that the nonlinear feature map is equivalent to the noisy linear feature map, then you are essentially dealing with, again, a Gaussian problem. And then with my students, we analyze for the Gaussian version, the empirical, the high dimensional limit of the training and testing error, and so the exact form doesn't really matter. The point here is that the training and testing error in the high dimensional proportional limit, they converge to deterministic quantities that can be computed by solving some fixed point equations. And the technical tool that we use, I want to mention that some of the idea was also used in some related papers about special settings of this kind of empirical risk minimization. Now, here is just some simulation to demonstrate this equivalence. Here, the green curve and the blue line correspond to the theoretical training and testing error of these two models. And we also overlay on top of the curve the actual simulation results, where the orange dots are for the original nonlinear feature model, and the crosses are the corresponding results for the linear noisy Gaussian model. You can see clearly they fall right on top of each other. There's, the dimension here is about 1,000 and 1,000, and D and P are proportional to 1,000. And the point here is that by analyzing the linear Gaussian model, you can get to these theoretical predictions. And from these theoretical predictions, you can, for example, get insight about these kind of non-monotonic behavior of testing errors and so on. But I'm not going to focus on that. My main point is, in principle, how you would analyze these and how to prove that the Gaussian model and the nonlinear feature models are asymptotically equivalent. All right. So I want to briefly mention that the main technical tool for analyzing the Gaussian model, because the Gaussian model involves analyzing a high-dimensional optimization problem involving Gaussian vectors, and the main technical tool that we use is now the standard Gaussian comparison inequality. For those of you who are not familiar with Gaussian equivalence, Gaussian comparison inequality, what we are dealing with are two Gaussian processes. The one on top involves a matrix with ID Gaussian entries. And then you have two parameters, which are two vectors, U and W. Okay? So you have a quadratic form plus a function of W and U, and this is a Gaussian process indexed by these two vectors, W and U. And I'll explain, where this Gaussian process comes out from the optimization problem. And there is a different process indexed by the same set of parameters, W and U, and we call it Y. And Y is, again, a Gaussian process, but instead of having C, a Gaussian vector driving the process, Y is driven by two Gaussian vectors, G and H. Okay? In principle, Y is much simpler than X because these Gaussians come in the form of vectors. Okay? Now, why do we have these two Gaussian processes? Because original empirical risk minimization problem, if you're dealing with a convex optimization problem, you can write out the convex view, and then you can convert the minimization problem as a mini-max problem. And the mini-max problem indeed involved the original Gaussian process X. Okay? So essentially, studying the testing error, training error of Gaussian model is equivalent, or it is sufficient to estimate the mean-max value of this particular Gaussian process with respect to, driven by a Gaussian matrix C. Okay? And then there is a different version Y, which is driven by the two Gaussian vectors, and then there's a corresponding min-max problem for Y. Right? Now, the classical Gordon's inequality says that you have this inequality. For any constant C, the probability that the original problem, which I call the hard version of phi, less than C, is bounded by 2 times the probability of the easy version less than C. Okay? So this is inequality. But how do we use this inequality? In principle, in many cases, this easy quantity is concentrated around a constant. And then what this inequality is saying is that the easy version, the quantity that you can calculate, essentially serves as a high probability lower bound the original hard bound. So you have one bound. And this is a fairly flexible type of result, and you can even use it to handle non-convex optimization problems. But the problem, the drawback of this bound is it's one-sided. You can only show one-sided type of inequality, but in this work by Stochastics and co-authors, they considered a special version of the Gaudin's minimax theorem, where if you are dealing with a convex optimization problem, then you get to fit these inequalities around, what you get are two-sided inequalities. And then if you have two-sided inequality, and if the ED version, you can show the ED version concentrates around some constant, then the hard version also concentrates around the same constant. And the point here is the ED version typically is much easier to analyze because it is only driven by two Gaussian vectors. So we have a separability to exploit and so on. So this is a pretty commonly used tool these days for analyzing the Gaussian theorem. All right. But the question is how to prove the equivalence conjecture, because so far we are only using this conjecture or equivalence as a given observed property, but we want to prove it. So I want to highlight the main idea behind the proof. Again, we have two versions, A and B. A is a linear version, and B is a noisy linear mapping. First of all, some intuitive explanation why we would expect the A version and B version to have asymptotic equivalence. What you can do is you can calculate the expectation of A and expectation of B. So different columns A and different columns B are all independent. So let's just look at each given column A versus each given column B, we can call AI, BI. You can calculate the first moment, which is a vector. And if you choose mu0, mu1, mu2, the coefficients correctly, then the first moment vector essentially equal to each other. You have a matching first moment. And you can also have essentially a matching second moment. Okay, so what we are saying is, in terms of random vectors, the vectors coming from A, vector coming from B, they have matching first two moments. Okay, right. And then we can say this, then A and B are equivalent because of universality. It's very similar on a high level to the example that we showed at the beginning of the talk. You are matching two moments of these high-dimensional random vectors. Right? Okay. And here, generic F essentially means that what we require is different, in this case, different rows of F, because you have a row of F in a product with your data set. Different rows of F are essentially orthogonal, and they have essentially constant norm. Okay, and then the different rows of F being essentially orthogonal make it possible for us to calculate, approximate the covariance matrix of A by doing Taylor expansion. C. All right. All right. But I want to provide a different, the original viewpoint is how we initially analyze or calculate the covariance of A and B. But there is a much more convenient way of doing all these kind of calculation if you use a special type of polynomials, for example, Hermite polynomials, because you're dealing with Gaussian data sets, and then Hermite polynomials are orthogonal polynomials with respect to the Gaussian measure. So you can consider a set of polynomials. And then these are the first four of these, and these are how they look like. And the point here is that these polynomials are orthogonal if you have the weight function being a Gaussian PDF. Now, suppose our linearity sigma of x is a scalar function. It can be approximated by a finite linear combination of these Hermite polynomials. Okay? And because we are applying sigma independently on each entry of this matrix, then we can write original A as a linear combination of these H matrix, where each H matrix is just applying one of the Hermite polynomials on the matrix, right? So you have A is equal to a linear combination of all these H.
So you get entry-wise, right?
Entry-wise, yes, entry-wise. Yeah, everything now is entry-wise application.
So what is the symbol of X?
So here, F is deterministic, and X has independent. So the simplest assumption is that X has independent column. Each column, for example, is ID Gaussian, or is drawn from the sphere uniform. But these kind of assumptions can be simplified, can be essentially weakened. For example, you can assume they are ID sub-Gaussian random vectors.
So on the previous slide, you were taking expectation of entries of A, right? They depend on S and X.
But yes,
Right,
so when we talk, on the previous slide, when we take the exploitation of A, the randomness comes from X. So here we are assuming F is deterministic, right? F is deterministic, so there's nothing about that, right? So the exploitation here, the exploitation of the second moment will come out as mu1 squared transpose F, plus everything. Right. So coming back to this point, so we can decompose the linear matrix A and the linear combination of these H matrix, where each H is applying entry-wise this polynomial onto the matrix. And essentially, the Gaussian equivalence principle is saying the following equivalence. Once you have written A as a linear combination, we can do a matching. We are saying that A is equivalent to a version B, where B is a linear combination of H0. You copy the first degree 0 Hermite polynomial, which is a constant, and degree 1 Hermite polynomial. Just to remind you, degree 1 polynomial is a linear function, so you have a linear function here. Then starting from the second H2 and H3, you just replace H2 by an independent Gaussian matrix, H3 by another independent Gaussian matrix, and so on. So this is really what the equivalence is saying. Right. And what about expansion coefficient mu0, mu1, mu2? We can see that because we are writing sigma in terms of these orthogonal polynomials, and these are orthogonal polynomials, so the expansion coefficients are exactly just in a product between sigma and each of these orthogonal polynomials.
So are the entries of F normalized to have some kind of like column energy one?
So here, the entries of F do not need to be exactly normalized perfectly. For example, here we're assuming that you can have for 1 plus small.
Oh, I see.
Yeah, 1 of the root p factors. Yeah, because in this linear proportional regime, having this 1 of the root p difference will not be.
Yeah, just trying to understand that you're using orthogonal polynomials with respect to the Gaussian measure, right? But
yes.
What is the Gaussian measure? Okay, it's because
the Gaussian measure comes from either product between F and X
or
from
C, right?
So here we are, if you theoretically assume X is Gaussian.
Yeah, that's another problem.
Yeah.
Okay.
But if you have ID sub Gaussian, then you come from C. Exactly.
Okay.
Yeah. All right. Okay. All right. So. So coming back to this equivalence, this is really, to me, exactly what is going on. You can always decompose a linear function as these linear combinations, these polynomial versions of matrices, and then these polynomial version matrices can be replaced by starting from H2 by a Gaussian. Okay, and because these 3 are independent Gaussian, you can combine them as a single Gaussian, and that's why we have a single noise component. I want to mention that this kind of phenomena appeared in random matrix theory before. To me, there are of course papers studying random matrix theory. Of course, come from Kernel method earlier, but in a setting that is the closest to our setting is a paper by Chen and Singer. They studied the spectrum of a random kernel method, and then their analysis implicitly implies some sort of similar phenomenon, although they didn't mention it, but their analysis implies this equivalence in terms of spectrum. So A and B will have the same spectrum, but what we are saying is that the equivalence of A and B go way beyond only their spectrum. You use A and B for empirical risk minimization, you have the same performance. Okay. So how do we understand this? To me, the most convenient way to look at this orthogonal polynomial and taking their moment is just to look at the spherical harmonics. So here, HK, again, the Hermite polynomials, and Hermite polynomials are close to some other set of polynomials, so-called Gegenbauer polynomials. So Hermite polynomials, what we're saying is Hermite polynomial Hi, Hj, and then there is a parameter Xi, right? We must have this type of also normal property where here Xi is just a Gaussian random variable, right? But then you can define a closely related class of polynomials, so-called Gegenbauer polynomials. What you do is Qi, let me call it Xi bar, and Qj Xi bar is equal to delta ij. But what is Xi bar? Xi bar is the following. So suppose you have X drawn from uniform distribution from the d-dimensional sphere, right? And then Xi bar is just equal to x1 times square root of d. Okay? So we can see when d is large, then the law of Xi bar is essentially a Gaussian distribution. But still, for finite d, there's a tiny difference between these two measures, so there's also a tiny difference between the coefficients of the so-called Gegenbauer polynomials and Hermite polynomials. But if you take d go to infinity limit, these two converge to each other, right? So that's why we say when d go to infinity, then you have this result. But if you have finite d, then you can just replace the Hermite by the Gegenbauer polynomial. For Gegenbauer polynomial, there's this very, very nice set of so-called addition rule. You can write, this is a linear transformation of inner product of two vectors. You can linearize it as an inner product of two higher dimensional feature vectors, where the entry of these feature vectors, y, k, a, are spherical harmonics. They are exactly spherical harmonics of this function, this vector f. So let me just, Hermite polynomial spherical harmonics. And then these f tilde and x tilde are just normalized versions of original data vector. Right. So if you assume your original data is already coming from the sphere, then you don't need to normalize these. And then if you assume f is also perfectly normalized, then you just have the same version. Again, the point here is that this formula allows you to linearize a linear inner product, okay, in a higher dimension. But this is essentially just the idea of Kernel method, right? You apply a linear function, and then it's a higher dimensional space, it's a linear function.
Sorry, can I ask another
Yes.
question? So on the previous slide, I think P had many terms, right? So like,
But you start somewhere.
yes.
So summation mu3 h3 up to mu l hl. And then there's mu3 z3 up to mu l zl for L finite, whatever finite. And then because z2, z3 up to
So you
zl
just
are
lump them together?
independent, then they can be combined as a single.
So it's a different mu2 from mu2 you used before?
Yes, that's right, yes. The other mu2 is a square root of summation mu2, mu3.
Yeah, okay. I understand. I just wanted to check. But sorry, but why do you truncate expansion at the finite?
This is just to analyze, so the argument, general argument is you first prove the equivalence between A and B for finite L, because, and then suppose sigma is a finite degree polynomial, and then you use a different argument to say that I can approximate those security large enough degree.
It's a two-step.
Yes. Because typically, if you have a finite L, you can get very detailed control of the error of the approximation. Because so some of the bounds depend on the degree of L. All right. Okay. So here we have this formula, but one more property that makes this formula useful is the following. If your vector f or vector x are uniform distributed on a sphere, and then if you think about these spherical harmonics as random variables, they are uncorrelated. So if you calculate the correlation between pair of spherical harmonics for a different degree, and for within each degree for different entries, they have essentially this property. Okay. And then the Gaussian equivalence at a fundamental level is just to say that in a high-dimensional case, you get to assume all of these guys are ID Gaussian. If you assume this is the case, then you will immediately derive all the Gaussian equivalence type of results. And then, first of all, using this kind of decomposition, it's very easy to compute all kinds of moments. The moment formulas are becoming very, very simple. And you can also check that if you look at each entry, because of this formula, and these quantities they are not independent, but they are weakly correlated. And then you have this formula, and nk is a large quantity. And then that's why you have a Gaussian distribution coming out by some sort of central limit theorem. And if you check the correlation between different entries of HK, then you can see that when nk is large enough, when nk is much larger than n, then the correlation between different entries of this matrix are also weak. And then that's why you can approximate it by an independent Gaussian matrix.
It's because I mean high dimensions, right? I mean xj entries are going to be super small.
So
can they just directly prove this?
So what you are dealing with is HK Ij.
Yes.
And I belong to n, right? And j belong to p, right?
Yes.
And then here, what is nk? Nk is the number of spherical harmonics. Depending on k, suppose you are dealing with k equal to 2 or above, nk is essentially, in terms of order, is essentially d to the power of k over k factorial. And then if k is greater than equal to 2, and n and p are all order d, and then this is a much, much larger sum. I don't know if it's the same question.
No, I mean, I had something much simpler. I just thought that, I mean, do you actually need any of these expressions? Or can you just use HK to be strict, any non-linear bounded? Let's say just quadratic polynomial.
Yeah, so HK, HK, for
Can
example,
you just directly analyze
for
this?
H2, x is x squared minus 1 over square root of 2. Yes. All right, and then you have square root of 2 in a product, which is summation fa xa squared minus 1, right? And then you can expand this product,
Yes.
and then you can have something similar to the y case. But then the trick here
That's
is
what I'm saying. You don't actually need this gigapower business, right? If you just want to prove this.
I see what you're saying. I can tell you exactly what the challenge is. The challenge is the following. So suppose you expand this, right? And then what you get is summation a, b, fa, fb, xa, xb. Right. And then of course minus 1 is
XB are Gaussian.
so you can, let's assume everything is Gaussian, right? And then what is easy, if you look at this sum, right? This sum essentially have a d squared term, right? But then what is easy is you can write this sum as a summation of 2 parts. Summation a not equal to b, fa, fb, xa, xb. And then you have summation a equal to b, fa squared, xb squared, right? This is much easier because you have coordinates not equal, and then if you check the correlation, everything works out, right? So this term is essentially behaving like a spherical harmonic. Okay. But what about this term? This term is not being 0. So what you do is you have to say this is summation a fa squared minus 1 plus 1 and xb squared minus 1 plus 1, and then you do expansion, and then you get, so you have additional terms. And in principle, yes, you can do everything by bare hand polynomial, but the spherical harmonics just makes everything automatic. They're automatic or false. It's so much more convenient. But I agree with you, if you don't have, for example, if you have f and x are not coming from uniform distribution of sphere, so x is just I, the sub-Gaussian, right? Then you should use this solution. But you have to do actual work. Yes. Okay. I hope
No, thanks. So it was much deeper than I expected.
All right. So So we have, the point here is that you just treat these as independent gases. So and then what we proved in this paper was the following type of equivalence. So we're saying that if you are using A and B in empirical risk minimization, where you have a convex loss function, and you also have a strongly convex regularizer, and the weight matrix coming from with the independent Gaussian entries, and activation function sigma has bounded third derivative, and I want to mention this is a very big restriction. So we are assuming that sigma is a null function, for example, a tanh. I explained why we initially wanted this condition, but then in principle, what is stopping us from applying having a result for a more general sigma? Suppose you have these assumptions, and then what we can show is the following result, equivalence result. First, the first line in terms of a training error, what we are saying is for any constant C, the probability that the B version of training error deviates from C by epsilon can bound the corresponding A version. And it's a symmetric. And then you have the other type of inequality for B, A bounding B. Okay, so if we can show one of them is concentrating around a given limit C, then this inequality essentially says the other quantity for the A version must necessarily concentrate around the same constant. All right. And this is only for training, but there's a similar result for testing testing the evidence. So it's the same type of result. And there's also some sort of a finite bound. Okay. All right. I want to skip this because this is a bit simpler. So in the proof, there are two main components. One component is to show a version of central limit theorem. What we are saying is, first of all, if you have A random vector coming from the linear feature map, B coming from the linear noisy feature map, you want to first show a central limit theorem. That means if you take this linear combination with correct normalization, W is just any independent weight vector, and then they have to have a Gaussian law asymptotically, and this is something that is needed. But then the main step of our proof is just a Lindbergh approach, because we want to show the two ensembles A and B be equal, but A contains n different vectors, A1 to AN. B contains n vectors B1 to Bn, and then the standard approach is because all these A's and B's are independent, right? So you just do entry replacement. So every time you replace one of A's by B's, and then you do it n steps. Okay. And then this is creating a bridge between A ensemble to B ensemble. You do n different steps, as long as you can show that each step incurs a difference of size of small O of 1 of n. You do n steps, then you can show A and B are essentially equivalent. Right? So this is on a high level what is the main idea. Now to show that per step the amount of error that occurs is of order little o of 1 of n, what you need to do is to analyze so-called the lead one analysis of this optimization problem. You want to show that by changing one regressor, you are only doing a tiny perturbation of the original high-dimensional optimization problem. But yeah, so there are these are more detailed questions. Okay. So also want to say that this equivalence type of phenomenon is fairly general. In another work that my student did, we considered a setting where we want to understand the effect of noise injection during training. So what we do is, the first line has the original optimization problem. You have the data, you have the labels, right? But what if you consider a different training method where you augment your data by additional noise, and then but the labels are the origin label. Okay, so that means each actual input data now is becoming little l different columns, but they differ by the additional artificial noise you inject. Right? So this is the type of training sometimes people use and as a regularizer, and we want to understand this. And this can also be analyzed in terms of a Gaussian equivalence. What you do is you just come up with a more complicated equivalence model, but the point here is, again, you match the covariance structure and the first two moments. And then from this, you can see some sort of interesting phenomena depending on the number of noisy copies that you use in the training process. You can have different type of non-monotonic behaviors happening at different values. Okay? And there is also an equivalence. So what from analysis, what you can see is adding noise is equivalent to adding a special regularization to the wavelet. This is just as a way to show that the equivalence phenomenon is fairly general, right? I think I put all what I wanted to say, but I'll be happy to answer questions. If there's any detailed technical question, I'm very happy to answer. So the main point here is that what I presented today is an equivalence theorem for nonlinear random feature matrices. This is an instance. You can think about this as an instance of the universality phenomena, and this is also a very useful type of result, because once you have established universality, you get to analyze the problem in terms of original linear Gaussian setting, and then for that you have a lot of very mature, powerful tools to use for analyzing the problem. Okay, all right. Thanks for your attention. Yes.
Is the main point of like the utility of randomness the features in this analysis, this condition that like FF transpose was the identity?
Yes. What's the question?
So couldn't you just consider like a feature, like it seems like the Gaussian energy is being used in like the x's.
Yes,
right?
yes, exactly. The randomness is driven by x. So f is generic.
Yeah, so couldn't we just choose f to be the identity and forget about it?
So in principle, yes, but then in principle, I guess you can even create your own conjecture, because if f has different norm profile, right? And then what you will get in terms of the Z matrix. So there is a Z matrix. So here the Z matrix has a ID, zero mean, and unit variance, right? But if you have f with different profile, for example, norm of f can change at a scale much higher than 1 over square root of p, and then I think what you need to do is to replace Z by an independent Gaussian matrix, but then the variance of each entry has to have a profile. Okay? I would not be surprised if there's equivalence for this model, but it's more complicated to analyze.
So if n is of order d to the k, it seems like in your expansion, you will see up to k term, and then other f is noise.
Exactly. So we have a paper currently under review for the polynomial scaling case. It's a very similar story. But the technical challenge here is that if you talk about polynomial scaling beyond linear, then you have to be careful about what type of terms can be neglected, what type of terms that you have to keep, because the size is large. So typically, if you're dealing with a symmetric matrix of n dimension, n by n, right? And then for things to make sense, each entry, hij, must be of order 1 over square root of n, right? To make everything correctly normalized, right? So that means anything is a big O. Anything smaller than 1 over square root of n can be safely neglected. They will not impact the general spectrum. But what if n is much larger than d? So for example, n is d to the power 3, right? And then there are terms involving d, which initially, for example, you can say I get to replace the Gegenbauer by the Hermite because the coefficient only differ by 1 over d. That 1 over d might not be neglectable. So you have to be more careful about what you can throw away. Oh, okay. On X, right? So On X, I think it's possible. In principle, if you have X that is independent column, but for each column of X, you assume these are just ID sub-Gaussian, for example. In principle, this can be still done, and potentially also using what Yuri's question was alluding to, that you are dealing with essentially polynomials, but you can do actual expansion of polynomials. And then, but you have to be careful about these kind of issues. If A not equal to BA,